Hey, welcome back to The Explainer. Today, we're going to dive into something you use every single day, maybe without even thinking about it. Real numbers. Now, I know it sounds simple, right? But trust me, this family of numbers, it holds some really cool secrets. So let's get into it. All right, let's kick things off with a little puzzle. You look at these three things: pi, the number -5, and a fraction like 3/4. What could they possibly have in common? I mean, they look totally different, don't they? Well, believe it or not, the answer is they're all part of one huge, single family of numbers. So, to figure out that puzzle, we've got to build our number universe from the ground up. And that's exactly what we're doing in this first section. We're going to define what it even means for a number to be real. Okay, here's the official definition. Real numbers, they're basically the collection of all rational and irrational numbers. But you know what? A much easier way to think about it is this. If you can pinpoint a number on the number line, any number at all, yep, it's a real number. Simple as that. So think of this like a big family tree for numbers. You've got all these different types you've learned about over the years, right? The natural numbers you count with, integers that include negatives, fractions. Even those kind of weird ones like the square root of 2 or pi, they're all just different branches on the same tree. They all belong under one big roof, the real numbers. All right, now, even though they're all in the same family, there's this major split right down the middle, a line in the sand that divides all real numbers into two very distinct groups. And honestly, understanding this split, it's the key to everything else we're going to talk about. So what is this big split? It all comes down to a really simple idea. On one side, you have your rational numbers, and the clue is right there in the name, ratio. If you can write a number as a fraction, one integer over another, it's rational. Easy enough. But on the other side, you've got the rebels, the irrational numbers. These are the ones that just refuse to be pinned down as a simple fraction, no matter what you do. You know, another really cool way to tell them apart is to look at how they behave as decimals. A rational number is predictable. Its decimal will either just stop, like 1/8 becomes 0.125, game over. Or it'll go on forever, but in a repeating pattern, like 1/3 is just 0.33333333. But an irrational number, oh man, its decimal goes on forever and never repeats. It's just pure, beautiful, unpredictable chaos. Okay, so how do we actually work with all these numbers? How do we prove things about them? Well, mathematicians have this incredible toolkit, these powerful theorems that are like master keys. They let us unlock the secrets of how this whole number system works. First up, we've got a real powerhouse, the fundamental theorem of arithmetic. This sounds super fancy, but the idea is actually pretty straightforward. It says that any whole number that isn't already a prime number can be broken down into a product of primes. And here's the kicker. That combination of primes is completely unique. It's like a DNA fingerprint for every single composite number. No two numbers share the same one. Let's actually see this thing in action. Take a number like 84. What do? Well, let's start dividing by primes. It's even, so we divide by 2, and we get 42. Still even, so we divide by 2 again, and we're at 21. Okay, not divisible by 2, but it is by 3, which gives us 7. And 7 is prime. So there it is. The unique prime DNA for 84 is 2 times 2 times 3 times 7. That's the theorem right there. Next up in our toolkit is Euclid's division lemma. Now, this formula looks a little intimidating, but all it's really saying is something you already know. When you divide one number by another, you get an answer, the quotient, and sometimes you have a little bit left over, the remainder. It's this simple idea of focusing on that remainder that becomes the secret engine for finding the highest common factor, or HCF, between two numbers. And here's a little piece of logic that is just so crucial. It might seem a bit abstract at first, but check this out. It says if a prime number p can divide a number that's been squared, then p also has to divide the original number. So for example, the prime number 3 divides 36, right? And 36 is just 6 squared. So this rule guarantees that 3 must also divide 6, and it does. This little rule is an absolute secret weapon that mathematicians use to prove that a number is irrational. Okay, so we've got these awesome, powerful tools in our belt, but they're not just museum pieces, right? They're meant to be used. So let's see how we can put them to work to solve some classic math problems. So here's a big one. How in the world do you prove that a number like the square root of 2 is irrational? You can't just list out its decimal forever. So mathematicians use this super clever strategy called proof by contradiction. Think of yourself as a detective. You start by assuming the exact opposite of what you want to prove. So you say, okay, let's pretend the square root of 2 is a rational fraction. Then, using those master tools we just talked about, you follow that logic until you run into a dead end, a complete impossible contradiction. And if that assumption leads to something impossible, well, then the original idea must have been true all along. And here's another really practical use for these tools. Ever wonder if a fraction is going to give you a nice, clean decimal that just ends, or one that goes on forever? Well, there's a super simple trick. You don't even have to do the division. Just look at the prime factors of the bottom number, the denominator. If the only prime factors you see are 2s and 5s, that decimal is guaranteed to terminate. It's a neat little shortcut, and it's powered by that same fundamental theorem we just learned. So, we've walked through the whole family of real numbers. We've seen the big split between rational and irrational, and we've looked at the tools mathematicians use to understand them. But so what? Why does any of this actually matter to you? Let's connect the dots and show you exactly where you're going to use this knowledge. And here it is, the payoff. Everything we just covered maps directly to the kinds of questions you're going to see. You're going to be asked to prove that the square root of 2 or 3 is irrational, using that contradiction method. You'll definitely use Euclid's algorithm to find the HCF of two numbers. You'll have to use prime factorization to solve word problems. And for sure, you'll use that denominator trick to figure out if her decimal terminates. See? This isn't just abstract theory. This is your practical toolkit for getting the right answers. So, we've explored this vast, logical, and really beautiful world of real numbers, from the simplest counting numbers all the way to the wild, infinite decimals of pi. But it all leaves us with one final and kind of mind-bending question. If all of these numbers get to be called real, then what on earth would make a number imaginary? Well, that's a story for another explainer. Thanks for tuning in.